about the strategy or how to analyze RC circuit, source-free RC circuit. The key things was listed over here, where you need to know how to calculate your initial voltage. If given, then that is good. And also the time constant. The time constant here for RC is given by this equation, tau equals to RC. And at the end, for source-free RC circuit voltage response can be expressed as equation below. V of t equals to V naught. V naught is the initial voltage across the capacitor. E to the power of negative t over tau. Tau is given as RC. And remember that the value of resistor or the circuit, if you have combination of resistors in your circuit, at the end, to come up with the voltage response, you need to simplify your circuit to become like this circuit arrangement, which means you're going to have two elements, C and R, connected in, can you call it in series also? You can also call it in parallel as well. Because if you consider this in parallel, also can, and if you consider this one in series, also can. However, what you need to do is you need to come up with this kind of circuit arrangement, where the value of resistor here is not comes from a single value of resistor. It comes from, maybe if the original circuit have a few numbers of resistors, means that you need to combine all the resistors to become a single value and denote as your Thevenin resistor, or R equivalent, or RTH. So here, what you need to do is come up with this kind of circuit arrangement. Then it's easier for us to use these two formula. And from that voltage response, we also can determine our current. And also from there, we can expand our determination of quantities inside our circuit in terms of power dissipation and also energy absorption. So this is the thing or the equation of power and also energy absorbed at the resistor. You can consider as this equation. And I've already discussed about this, and the thing is that, remember, if there is a numbers of resistors in the circuit, means that you need to combine that resistors together and come up with a single value of resistors known as equivalent resistor or Thevenin equivalent resistance. Actually, what happened in RC can be applied in RL as well, except that in RL we consider the current. So here, same goes to RL circuit. We need to come up with this kind of circuit arrangement. We have two elements, inductor and also resistor. And again, resistor, if we have a number of resistors in our circuit, we need to combine all and come up with the value of a single resistor known as R equivalent or RTH. And maybe this part you can skip because the most important thing is that you need to know for current response in in RL circuit should be given by this formula, which is I of t equals to I naught. I naught is the initial value of the initial current value flowing through the inductor, and also the time constant is given by tau equals to L over R. That it is a bit different from what we've seen in RC circuit. However, the principle or the way we analyze the circuit, for example, in order to get R, we need to have a Thevenin equivalent resistor. So that's the thing that I think using the same principle as well in RC circuit. All right, if you look at example 7.1, I think I've already asked you guys to look at example 7.1. In example 7.1, in this question, V0 or voltage, initial voltage at the capacitor is given by 15 volt. And what we need to do, what the question asks is, what is the voltage across the capacitor or VC, and also voltage Vx and current Ix for t greater than 0. This is the strategy, only the strategy that I showed over here. If you want to have the complete solution, I think here maybe I'll try to share with you guys. Yeah. Can you see both? Okay, can you see both papers that are presented here?
Yes.
Opposed to a bit small, I think. Okay, anyway, this is the only the step. Looking at my slide over here, the main objective or our objective is to first determine the value of voltage across the capacitor. So to determine voltage across the capacitor, we know that the voltage response is given by V naught, V of t equals to V naught e to the power of negative t over tau. Then we need to find, our target is to find parameters in RC equivalent circuit. Why we need to find parameters in RC equivalent circuit? We know that the first thing we need to do is try to set up something which just looks like this. We have single resistor and a capacitor. And from here, we can determine the value of tau, and using the equation that we've seen earlier for voltage response across the capacitor, we can easily get our voltage response for t greater than 0. And for t less than 0, okay, it's given by the value of initial voltage given in the question. So now, solution is, our target is to get this kind of circuit arrangement. And the step is find the initial voltage. Don't have to find because it is given. And find the equivalent resistance, Thevenin resistance, and we can straight go ahead calculating the time constant. So from the time constant, we can write the voltage response across the capacitor, and later on, since we know what is the voltage across here, we can use voltage divider rule to calculate the voltage across this resistor. We divide, we know that from here, from the top up until the bottom is given by VC, so we can use this VC information to find the voltage across this 12 ohm resistor. Okay, if you look at the circuit itself, it's a parallel circuit, means that voltage drop at 8 ohm resistor and 12 ohm resistor. If you sum that two voltage drop, it is equals to VC. Same goes to this 5 ohm resistor. For example, if I ask about what is the current over here, so you can use the information of VC and divide it by this 5 ohm resistor to get the value of current flowing through this branch. So then don't be panicked. Have a look at the circuit arrangement carefully, and you know that this is a parallel connected circuit. Means that if you know what is the voltage over here, it's easier for you to get information for the other branches. So that's why we use voltage divider rule to calculate Vx. And since Vx is known, already been calculated, you can calculate the value of Ix over here using basic Ohm's law. So that's what's happened in the solution. Maybe the arrangement of the way it's solved is a bit different from my solution over here, but basically both objective is the same. So if you look at here, the first one is we first need to make circuit 7.5 conform with the standard RC circuit. Means that we need to come up with this kind of circuit arrangement. So since we have a few resistors connected in the original circuit, we know that the resistor over here should be R equivalent. Okay, the equivalent resistance or the also known as the Thevenin equivalent resistor need to be determined. Okay, how do we determine the Thevenin equivalent resistance? So we find the equivalent resistance or Thevenin resistance at the capacitor terminal, meaning that we try to remove this part first. We try to make this is as a terminal. First, terminal A and B, and try to find what is the resistance looking from these two terminals, A and B. In other words, we try to remove the capacitor first and try to find Thevenin resistance over here. And if you look at the circuit, this is A, maybe this is B, I call like this. From A, I have two branches, which is first is 8 ohm and another one is 5 ohm. Okay, this is settled and this one is settled. This is 8, this is 5 ohm. And again, if you go on go around the first branch, after 8 ohm, you will see that we have another another resistor, which is another resistance over here, and the resistor is connected to terminal B. Same goes to here. 5 also directly connected to B. So this is your 12 ohm resistor. So from here, you see that if you try to find resistance looking from terminal A and B, this is R equivalent. Okay. It is given by 8 plus 12 in parallel with 5 ohm resistor. So that's why we have 8 ohm and 12 resistor in series can be combined to give 20 ohm resistor. This 20 ohm resistor is parallel with 5 ohm resistor can be combined so that equivalent resistance is this value. And then you set up this kind of circuit. We have R equivalent information as well as this 0.1 farad capacitor. You can straight calculate the time constant is given by 0.4 seconds. It is coming from the product of R equivalent and the capacitor. Please remember this equation. I think you don't have any problem remembering the equation because of the nature of your assessment, which is using online. So you have opportunity to get into your notes and also textbook later on in your assessment. For previously previous students, maybe they need to remember this um, equation or this formula. I think you have a lot of advantage in that sense. Okay, now since we know what is the tau and we can put all information that we can gather all information inside our voltage response equation, where equation of voltage response is given by V of t. Okay, V of t equals V naught e to the power of negative t over tau. Okay. Now we know what is the value of tau, and we also know what is the value of VO. So VO is given by 15 and tau is given by 0.4. You just put inside your equation over here. And that is your voltage across the capacitor response. So please remember, this response is considered for response at t greater than 0. And later on, we try to find what is the value of Vx over here using voltage divider rule. And remember that if I put this one from A to B is Vc. If this one is Vc, okay, I think I try to remove this first. Vc that we calculated earlier. So what we're trying to do is we try to find what is the voltage at here. The voltage across here can be calculated using two options. Whether you know what is the current over here, whether you know what is the current flowing through this branch and then multiply it with this 12 ohm, or you can also use voltage divider rule. Basically, to find Vx and Ix, you can find either of the information first. For example, if you like to calculate Ix first, also can, because Ix is given by Vc divided by these two resistors in series. You combine these two in series, and then the Vc should divide by this resistor. Or you can use voltage divider rule according to this solution. It uses voltage divider rule, and later on use that voltage to calculate Ix. So that's for example 7.1. I think it's very straightforward this in this example. For example 7.2. You have any question so far? I think you already put some effort to revise the solution, so it's easier for you to understand what's going on in the solution, or what we expect, the explanation from the solution. Okay, for example 7.2, I proceed because I think we don't have much time today. All right, for example number 2, now we have a circuit consists of switch over here, and if the switch is labeled like this, means that at t greater than 0, okay, at t equals to 0, the switch will be open. In other words, for t greater than 0, this part will be will be neglected. I mean, will be 40 greater than 0, this portion is gone. You don't have this portion, only this part. Okay, if you look at this part, means that we have a source-free RC circuit for t greater than 0. And if you go through the question, okay, you find that you don't know what is the value of initial voltage or initial energy stored at the capacitor. So you need to find that information. In other words, V initial or VC, initial voltage across the capacitor, is not given. And for t less than 0, okay, when the switch is closed, the capacitor is an open circuit. Remember, last time we know that the capacitor during steady state, it will become an open circuit element. So looking at this kind of circuit arrangement, as well as the condition given in the question, what we know that, okay, during t less than 0, the switch is closed, and the circuit or the capacitor inside the circuit will become or not will become, it's already been an open circuit element. At t greater than 0, or starting from t equals to 0, this switch will be open, and we will end up with only this circuit connection, or this element is the only connected element in the circuit. Okay, so what I have in my slide over here, telling about how to the strategy, how to solve that that kind of problem. So here the target, it's still the same. We try to find parameter of RC equivalent circuit. Our main objective is to get a circuit which consists of only these two elements. Maybe I delete this first. Consists of these two elements. Okay. R equivalent, and this is C. Our main target is to get into this one. Why? Because from this circuit arrangement, or when we reach up until this point, we can easily calculate our tau given by R equivalent times C. So we need to find these two elements. I mean, the main thing is this R equivalent. Okay, before we get into that one, we know that for voltage response, this is given by V naught, sorry, not V naught, V of t. V of t equals to V naught e to the power of negative t over tau. So here, we need to calculate what is the value of our V naught, or initial voltage. And the way we calculate the initial voltage is by looking at the circuit before it is before the switch is open, or before t less than 0. So for t less than 0, the switch is closed, means that the capacitor will be open circuit, and we try to find what is the voltage drop across here. Okay, voltage drop across here, if this is an open circuit, meaning that there is no current flowing through here, I will be equal to 0. And the voltage VC, basically the voltage drop this is the voltage drop across, oh my goodness. Voltage drop from here to here. Okay. So that's why if you look at this solution, to find the capacitor voltage, i.e. the open circuit voltage, is basically finding the voltage across this 9 ohm resistor. So now we use voltage divider rule to find what is the voltage across here, because you know current over here is 0 and voltage VC is basically voltage from this point up until this point. Now this 15 volts we calculated can be considered or is considered as our voltage, initial voltage across the capacitor. Or that's why here it is identified as VC naught equals to V naught equals to 15 volts. Later on, we try to work out the tau by analyzing the circuit at t greater than 0. If you consider time greater than 0, means that the switch over here will be open. And again, I already mentioned just now, the circuit at the left hand side can be considered neglected. The only circuit that the only element that we consider is these 3 elements. That's why you see here the circuit had become like this for t greater than 0. Okay, for t greater than 0, you know that if you try to compare this circuit and this circuit, okay, you try to find what is the equivalent resistor over here. Basically, the equivalent resistor you can find using the same technique that I showed just now, where what you need to do is you try to open this part first and try to find what is the resistor looking from this direction. Okay, looking from this direction. In other words, you will come out with something which is look like this, where this is 1 ohm and this is 9 ohm. So it is easy that we know that to calculate what is the value of resistor over here is given by these 2 elements connected in series. So that's why here you see that R equivalent is given by 10 ohm resistor. And since you already know what is the value of R equivalent and also the value of capacitor, it is easy for you to calculate the value of tau. For RC circuit, tau is given by R equivalent times C, and you will get the value of tau given by 0.2 seconds. And again, using the equation that we know from the formula for RC circuit, we can calculate the voltage across capacitor given by 15 or the VO initial voltage times e to the power of negative t divided by tau, or 0.2 volts, so 0.2 seconds. So the overall response is in volts because this is voltage across the capacitor. Now, the question basically asking about initial energy stored in the capacitor. So to calculate the initial energy stored in the capacitor, basically we try to, we only need the value of VC naught, or initial voltage at the capacitor, and information of capacitor value. So we can simply calculate the energy stored. So for the second question over here, or if this is the question of your test, if this is 10 mark, maybe the second part contribute about 2 to maximum is 3 marks lah. I think it's about 2 marks, and the rest of the marks, for example, if initial energy 2 marks, the other 8 marks contribute from this V of t, finding V of t. So please remember that although you can calculate this part, initial energy, However, find V of t over here is very crucial, where you need to find the answer for that one also. Okay, now 7.4, I think you can have a look by yourself later on. This is for RL circuit, the same strategy that I've explained earlier being applied in this example. Have a look, maybe later on during revision session, maybe towards the end of our semester, when we try to prepare for final exam, we will have a look back at this example. But for time being, please try to understand this example and maybe a few more examples in your textbook regarding source-free RC as well as RL circuit. This is considered as RL because we have one inductor over here. Okay, that's for example 7.1, 7.2, and 7.4. Do you have any question so far? Can I get response from you guys? Do you have any question?
No.
No. Oh, okay. Please be aware that this topic will be asked in your final exam. So although now it's not that important, I mean for preparing your test one. However, if you leave this like, okay, later on I will try to, maybe later on you will forget or you will find it very hard to understand what's going on for source free or for this topic. Okay, that's for source free, and this is the example of final exam question that I'll talk about. So if you look at here, this is a simple one, source free. However, there's majority of students cannot answer this question. I don't know why. Although this is very simple, if you look at the example over there, previously I showed you, I think that example is more difficult compared to this one. This is something which is same like example 7.1, except that the values over here are a bit different. But believe me, last time, majority of the student just, okay, this I cannot answer this one. It's very difficult. I don't know why. Maybe because of this situation, because they are preparing for their test and they tend to like I don't know what to say about that one. They try to make it this one. Okay, later I will try to understand it back, but it's not gonna happen instantly. Okay, let's take 5. I think later on, maybe we take 5 after this. After I explain about the functions and so on, maybe we can take 5 later on. Okay, that's for the first part. The first part consists of source-free RC as well as source-free RL circuit. Now we move on into the second part of this week's topic, which is RC RL circuit with source, or sometimes it's called as step response RC circuit or step response RL circuit. That means the circuit during t greater than 0 is supplied with a voltage source. Earlier, we know that at t greater than 0, we don't have any voltage source. We just have a simple voltage response of voltage across capacitor or current response for the current flowing through the inductor. It's very simple for source free. But now we have voltage response. What does it mean by voltage response? Later on, maybe I will explain. But before that, we try to understand the important definition or important function for step response or voltage source or voltage or current source given in our circuit. Okay, now we try to understand what is a singularity function. Means that singularity function serve as good approximation to switching on and off a voltage. Previously, you see that voltage, we have switch in our circuit where we at t greater than 0, the switch is off or the switch is on, turn on, and so on and so forth. But we can replace that kind of source or voltage or current source by using a singularity function. Singularity function is here it says that as a good approximation of switching on, switching off a voltage means that if you have switch and source, you can also represent it as singularity function. Here we have three most common singularity function. We have unit step, unit impulse, and unit ramp. For your case, I will not ask unit impulse and unit ramp for your case for this course. Only circuit consists of unit step. However, you also need to understand what does it mean by unit impulse and unit ramp. It's useful maybe later on in your second year, third year, means that, oh, I've already learned this one. This one is unit impulse and this one is unit ramp. So if question in your circuit, I'm not going to give you a question which involves unit impulse and unit ramp connected in your circuit. However, maybe I could ask you about, okay, draw unit impulse waveform or unit impulse response. Draw unit ramp response with respect to graph with respect to t. So maybe I could ask you that way, but in terms of analysis, I will not ask you on that one. Okay, what does it mean by unit step? Here it says that unit step is a function that maintains a constant value before certain time, then change to another constant afterwards. So here we have like, this is what you call as unit step, from one level to another level. Maybe from this level also can get into zero response over here. In mathematics, we can express unit response using this equation. What does this equation mean? U of t equals to 0 at t less than 0. So look at this diagram. At t less than 0 means that this part. U of t, value of u of t is equals to 0. And 1 for t greater than 0. So at t greater than 0, from 0 towards t towards infinity, you see that the value of u of t is equals to 1. So mathematically, we can express unit step using this function. And if we have like a shifted response, or the unit step itself will be shifted either towards a positive side of our time or negative side of our time. This is how we write down the equation of unit step, where you see here for figure A, okay, where being shifted towards right hand side, we can use equation over here, u of t minus t naught. T minus t naught here value is a positive value, and 0 for t less than t naught, and 1 for t greater than t naught. And for figure, next figure, that is figure B, where we have t naught value is negative. seems like same like when we try to shift our unit step towards the negative side of our time or towards left hand side. So what happened here, we shall write u of t plus t naught. Basically this is minus t naught and equals to 0 for t less than t naught and 1 for t greater than t naught. Bear in mind that this kind of equation given by this kind of response. So the unit step is like shifted to left hand side. That is called a delay in switching. So switching maybe delay about 2 seconds. We can represent it like here t naught equal to 2 seconds maybe. For this diagram, maybe we switch it in advance or a bit early. For example, early by 2 seconds. So early by 2 seconds means that the -2 is over here. So we can write that it in terms of mathematical expression, we can write like this. Okay. Unit impulse. Okay, unit impulse is basically or can be illustrated using this kind of diagram. We have derivative of the unit step. Okay, in other words, if you have unit step and then you differentiate it or do some derivative on the unit step, this is what you will get. A response which is known as unit impulse. So here at t less than 0, the response is 0. Okay. At t greater than 0, also the response is 0. And it is undefined or the value is too big. We can also say it as undefined. At t equals to 0. And if you try to like shift this undefined value, you might also need to modify this part where for shift towards the right hand side of your time or towards positive value of time, maybe it will become t minus t naught. If you try to shift it towards the left hand side, it will become t plus t naught. So this is a general case of unit impulse where we don't have any time delay over here. And for unit ramp means that we're going to have a ramp response. Ramp response means that we're going to have a gradient over here. And the gradient is always given by t. Okay? Sometimes maybe this is an ideal unit ramp. If you say that it is a unit ramp, means that value of the gradient over here is always given by t. If it is like people ask you about what is ramp input. Ramp input means that if here is unit ramp, for ramp input, the value over here not always equals to t. Maybe it's depends on the gradient. Maybe 2t, 3t depends on the gradient over here. But if you ask about unit ramp, unit means single. Single means it's gonna have t over. You're gonna have t over here as your response for t greater than 0. So this is the example of unit ramp. Okay. Any questions so far before we took some time for us? We take 5 and we come back in the session at 12:03 noon. Okay, if you don't have any question, maybe we stop for a while, about 5 minutes, and later on we will continue on step response of RC and as well as RL circuit. at 12 3 noon or 12 3 p.m. Okay, see you later on. Okay, welcome back. Are you there?
Yes, over here.
Okay, thank you for your response. Okay, now we try to continue our lesson where we extend our knowledge into a step response of RC circuit. Previously, we looked at circuit which don't have any sources at t greater than 0. Now, you see that if you look at the circuit over here, at t equals to 0, the switch will be closed, and the circuit consists of three elements, which is R, T, as well as our voltage source over here. And as I mentioned earlier, the voltage source and this switch can also be replaced using a step function. Okay, that's why the circuit response is known as step response. Okay, we have a look at this kind of circuit where we have three elements at t greater than 0. If we assume that initial voltage is given as VO, okay, and we blah 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 try to apply in KCL, and later on try to analyze the circuit at t greater than 0 by integrating and also simplifying some of the equations. Finally, you will end up with this voltage response across the capacitor. So I don't think that this part is like it is compulsory for you guys to know, but if your mathematics is strong, I think it's easy for you to understand this part. However, if not, the way my strategy to answer this kind of problems, I try to really understand what does this voltage response tells me. So from here, at the end, to get what is voltage response across the capacitor, okay, V of t is given at, for t less than 0 is given as the initial voltage. So because at t less than 0, we assume that this capacitor has a initial voltage of V naught, and after switch is closed or at t greater than 0, this is the response of the voltage across this capacitor. It is given by Vs plus V naught minus Vs e to the power of negative t over tau. If you look at the response of the circuit at t greater than 0, there are 3 parameters that you need to determine in order for you to have a complete value or complete response of the voltage across the capacitor. The first one is V naught. Okay, we already know this is initially charged. So if in the question the initial voltage is given, so it's easy for us. This one is considered done. The thing that we need to really find is what is the value of tau, as well as what is the value of Vs. Vs is basically the value of voltage over here. Okay, the value of the magnitude of voltage over here, right? Okay, one more thing. Look at these two circuit arrangement. The first one, if you see that I also mentioned about these two elements, voltage and the switch, can be replaced as a step function. So in this diagram, you see that Vs is multiplied by U of t. Remember that U of t, okay, U of t is given by here, U of t Okay. The different color. This is known as U of t, where this is t, the vertical axis is U of t. So U of t value over here should be 1 unit step response. So that's why we have, let's say this one is 10. Okay, this value should be 10 U times U of t, and voltage response over here. Okay, let's say I plot it as a Vs. A Vs, the value here is 0, and will reach 10 volts at t greater than 0. So this is t. This is how the response of VSU of t looks like. Less than 0, or t less than 0 at negative time, or t before the switching, the voltage is given by 0 volts, and after the switching, or at t equal to 0 and t greater than 0, the value of voltage is given by 10. Okay, now as I mentioned just now, you only need to remember this part. This part maybe you can have a look later on in your textbook. Okay, this is known as a complete response. So in other words, I would like to say that V of t that I boxed over here is a complete response of voltage across the capacitor. So now, if you look at the response, okay, the response of this equation, okay, if we try to plot this equation with respect to time, this is what the response looks like. For example, the first part here is for t less than 0. For t less than 0, if you look back, the value of V of t is V naught. So here, you see that V naught for t less than 0. Maybe I'll try to draw here. This part is for t less than 0. And the one that you saw in right hand side and being constant at V of s. So here, this part, maybe towards infinity, yeah. So if we consider towards infinity, maybe this is a bit longer. And this is for t greater than 0. And this kind of voltage response can be called as the natural response of the capacitor, or maybe inductor later on. We will see on it, due to the energy stored in it. Okay, and the second part is force response. Second part means that the natural response basically around this area, the transient part, the natural response, and the one that you see on the steady state portion here is called as force response. It's due to the independent source. You see that the independent source here is V of s, and this part is considered as your force response. Okay, anyway, if you don't know what is natural response, what is force response, you still can answer the question for this topic, since you know how to find the parameters inside the equation, V naught, Vs, and as well as tau. Okay, complete response, as I mentioned earlier, when we combine both natural and force response, we will get our complete response. And another perspective, maybe you can look at as transient and steady state response as well. So either one lah, either one. But basically, if you know this equation, then it should solve the problem. And in general, what we try to when we try to write down our voltage response when t greater than 0 for step response RC circuit, this is what we should have in mind. See here, we have V infinity over here. Basically, V infinity is also known as Vs, or the supply voltage. Supply. Or sometimes known as VSS. This is the steady state. The steady state voltage. Oh my goodness. Right. Actually, this equation is the same equation you've seen over here, except that I change this Vs into V infinity, and the rest will be the same. So this is the complete response of voltage across the capacitor for t greater than 0. And again, V0 over here is the initial voltage across the capacitor at t less than 0. Okay, we straight into our example 7.10. If you look at 7.10 example, I just show you the procedure, how to solve the example. Maybe I put it here. Boom. I put it a bit smaller. Okay. Now, example 7.10 also can be found in your textbook, page 275, RC with source. Okay, look at this example. Do you have? Okay, no other. All right, now. Okay, according to the question, it says that the switch in figure 4.3 has been in position A for a long time. At t equal to 0, the switch moved to B. Determine V of t for t greater than 0 and calculate its value at t equals to 1 second and 4 seconds. Okay, it says that for t less than 0, okay, means that we should consider this circuit. Okay, how do I change this one? Yeah, the color over here. How do I change the color? Can I change it? Tools, properties. Okay, here. Okay, if I consider t greater than 0, for t greater than 0, we should consider the circuit which looks like this. We have two types of circuit that we need to analyze. Okay, first we analyze at t less than 0. Why? Here, for t less than 0, we try to find what is the initial value or initial voltage across the capacitor. And looking at the circuit, during initial stage or at switch at position A for a long time, means that the capacitor itself will become an open circuit element, okay? An open circuit element, because it has reached its steady state stage. So if this is an open circuit, means that the circuit will be looks like this. I'll try to draw it here. The circuit will, oh, maybe I need to change into red color. Red color. Okay. At t less than 0, we should have a circuit which this is 3 kilo ohm, then 5 kilo ohm over here. We have voltage here is 24. This is 3, I put this as 3. This is 5. And this is the open circuit part. This is the open circuit. Oh. What's wrong with this? Open. Since it is open circuit, means that the voltage across this capacitor basically is the voltage over here. If you would like to know what is the voltage over here, try finding the voltage across this 5 kilo ohm resistor. That's why in this solution, you see that we try to find the voltage across the 5 kilo ohm resistor using voltage divider rule. So here it says that the capacitor for t less than 0, the switch is at position A. The capacitor acts like an open circuit to DC, but V is the same as the voltage across 5 kilo ohm resistor. Hence, the voltage across capacitor just before t equals to 0 is obtained by voltage division. That's why it used voltage division over here, because you know here is 24 and here the current is equals to 0 because of open circuit, and the voltage you see over here is basically the same as the voltage for this 5 kilo ohm resistor. So voltage across here is considered as our initial voltage of the capacitor. Now, step number 1 or procedure number 1 finished. Okay. Procedure number 2, we try to analyze the circuit for t greater than 0. For t greater than 0, try to use blue color this time around. Okay. For t greater than 0, the circuit that you should consider is supposed to be looks like this. Okay, and there's capacitor, and we have 4 kilo ohm over here, and we have 0.5. Oh, quite difficult. Difficult to write 0.5. 0.5. This is 4 kilo ohm. 0.5 millifarad. This is 4 kilo ohm. And the voltage over here is voltage here is 30 volts. 30 volts. Now, see, we have a circuit arrangement consists of resistor, capacitor, and our voltage supply. This is what we need. If we have a few more resistors connected in series or in parallel, what we need to do, we need to combine all those resistors and put it this way. I mean, put it as a single value of resistor. It means that we need to have a Thevenin equivalent resistors. Same goes to capacitor, but in your case, maybe capacitor, I'll try to put only one capacitor in your circuit. However, for your information, just for your information, if you have more than one capacitors, means that you also need to combine all the capacitors so that it will rearrange, or we can build up a circuit or draw a circuit which looks like this. Only 3 elements over here. Why this thing is important? Because we try to what we try to do, we try to use that kind of circuit arrangement in order to use the equation that we seen earlier. So we need to have this kind of circuit arrangement in order for us to use this formula. So this formula comes from this kind of circuit arrangement. We have voltage, resistors, and circuit. Capacitor. Right. Now, when we try to find the value over here of R and C, I think C is quite straightforward. However, for RTH, okay, what happened over here? Here it says that for T greater than 0, the switch is in position B. The Thevenin resistance connected to resistor RTH equals to 4 kilo ohm. So something which is missing over here, it should say like to find RTH, okay, RTH over here can be found by considering this kind of circuit arrangement. Okay. RTH means that this is a capacitor, earlier capacitor, then we remove that capacitor, we try to find RTH over here. And for the voltage supply that we have here, should be treated as a short circuit. Remember that in Thevenin equivalent circuit, to find Thevenin equivalent circuit, for voltage source, what we did was we zero all sources. For voltage source, we treat it as short circuit. For current source, we treat it as open circuit. So this is how we find RTH. And RTH, looking from this terminal, or looking from this is the capacitor part, where we remove all the capacitor in order for us to find the resistor, Thevenin resistor. So the RTH over here is given by R, R. Maybe we can put R equals to 4 kilo ohm. 4 kilo ohm. That's why here you say RTH equal to 4 kilo ohm. Not just simply saying that this is RTH equal to 4 kilo ohm. What happens if I have this another resistor over here? What happens? If I have a few more resistors, maybe I put it like this. Okay. Maybe here I have a resistor, and maybe I have another one over here. What happened? So this is what you should do, where you should consider removing the capacitor and all the sources inside the circuit. You put it as a short circuit for voltage. For current, you put it as open circuit. So, and then you find what is the resistor value looking from the capacitor that you removed earlier. So this is what happened in the circuit. And to get tau, tau is simply given by RTH times the capacitor, and you will get tau value equal to 2 seconds. And since we have tau over here, we have V naught, okay, and also we also know what is the value of V infinity. Since the capacitor act like an open circuit at steady state, means that V infinity equals to 30 volt. I think this one is something which also hidden in the text. Look at the circuit back. If you have circuit which is look like this, yeah, you have capacitor over here. Yeah, resistor R. This is capacitor, and this is the voltage. If this kind of circuit is remain for a long time, meaning that you're not moving, you're not cutting out the current supplied to the capacitor. What will happen to the capacitor during the steady state? The capacitor will behave like this. Maybe I change the rate. Okay. What would happen to this circuit is that, okay, this one, the capacitor is there, but the, oh, okay, this capacitor would become an open circuit. So the circuit basically during steady state would looks like this. And this is positive, negative, V, and V at steady state we can consider it as V infinity. Okay, V infinity over here, and V infinity over there, or V infinity of equals to V state, steady state. Basically, it's the same value that we've seen over here, ES, or in this case, it is 30 volts. 30 volts is equals to this value, 30 volts. Because this is an open circuit, and open circuit voltage over here is the same voltage looking from this voltage supply. Because current here is 0, the voltage drop across this part, this terminal at steady state is equals to 30 volt or voltage supply that we have in the circuit. So that's why here it says that V infinity equals to 30 volts. Not just simply saying that, okay, this one, this 30 volt is equals to this voltage lah. No, it is because of this kind of what do you call it, approach, or this kind of circuit arrangement. Okay, now we know what is V infinity, we know what is tau, we know what is V naught. Just plug in all the values in your voltage response equation. So V infinity is equals to 30, V naught equals to 15, V infinity is 30, times e to the power of negative t over tau is given by 2 seconds. So this is the complete response, or the final solution of voltage response across the capacitor. And remember that in the question also asked about calculate its value at t equals to 1 and t equals to 4. I think that's very easy. Just replace t to be 1, and also at t equals to 4, just replace this part as 4, and the t that you've seen over here replace as 4 at the down here, and 1 over at the top over here. So plug in your calculator and you can get its value in terms of voltage value, voltage magnitude. Okay, that's for example 7.10. There's two things that I think it is hidden over here. It is due to, it says over here, try to calculate RTH, and RTH is given by 4 kilo ohm. And maybe you're wondering how this 4 kilo ohm, how it gets 4 kilo ohm over here. So it's come from this circuit arrangement, And for VTH also coming from this kind of circuit arrangement where we consider V at steady state or V at T equals to infinity, T towards infinity, the circuit will behave like this because this capacitor will become an open circuit. Then voltage across the capacitor is the same voltage value looking from the supply. Okay, that's for example 7.10. Example 7.11, I think later on you have a look by yourself what's going on over here. I would like to continue on RL's circuit where later I will show you the example of our step response RL circuit. 7.2, 7.11, I've already put it in e-learning. You can also find it in your textbook. Have a look. And for RTH and VTH, please pay attention. For RTH, please remember you remove the capacitor and try to find what is the value of resistor looking from that capacitor part, capacitor terminal that you removed earlier. And all sources, you should put it as a short circuit or open circuit, depends on the nature of the source. For this example, the source is voltage, so that's why we put it as short circuit. And for if you have current source, you should consider as open circuit at this part. Again, for VTH, please redraw back the circuit and imagine if the circuit being kept for a long time, or when considering that T towards infinity, what would happen towards to the capacitor? Capacitor will open circuit, or capacitor will behave like open circuit, and then find the open circuit voltage across that capacitor, across that two terminals. Okay, that's some reminder for you guys in order to really understand what's going on over here, because I think the solution, there's something hidden over here. The equivalent circuit, if you don't have that equivalent circuit, you don't understand how does this V infinity come across. All right, for step response of RL circuit. I think if you understand the solution of RC step response RC circuit for step response RL circuit, it will be I think it's the procedure or the principle is same. Same goes to the one that we saw for source-free RC and RL circuit, where for RL circuit, what we focus is the current. Okay, now for step response of RL circuit, we should consider at the end, we will come out with this kind of circuit that we need in order for us to calculate the tau and also come out with the voltage current response or current across flowing through the inductor for t greater than 0. So for current, you should remember that current is given by Ohm's law. According to Ohm's law, current is given by Vs divided by, or not Vs, V divided by R, that will leads us to current. But here it says that in order for us to calculate the steady state current, okay, when steady state, what happened over here, or steady state means that this part can be also known as I infinity. Okay. During steady state, what happened to this circuit? For example, this is for t greater than 0. Okay. If you put it t greater than 0, for t towards infinity, this inductor will be a short circuit element. Okay. If this is a short circuit element, what is the current over here? Current over here is given by I steady state or I infinity. Okay, I I steady state. And I steady state here can be found just by looking a simple Ohm's law where you will use this information of voltage and this information of current. Okay, that is if this is a voltage. However, if this is a current, okay, let's say I put it like this way. Our job will be a lot more easier because let's say this is IS. Okay. I steady state or I towards infinity is equals to the value of a current source over here. Okay, remember that this ISS not always Vs over R. Depends on the nature of the source that you have over here. If this is a voltage, yes, of course, to find the current, you need to apply Ohm's law. However, if this is a current source, our life would be a little bit easier. But some students may think that, hey, how do I get ISS? I don't have this VSS, or sorry, I don't have the VS. Based on the notes that I have, to find ISS is by using Vs over R. That is for that kind of thinking is for actually for students who only read, remember, but he don't understand, he or she don't understand about the circuit. So if you just remember or if you just read your notes without really know what's going on in the circuit, means that you're not going to get it correctly. All right. Maybe this one, the important part is the initial value of the current. Maybe later on, maybe a little bit easier if we have a look at the example in just a while. Okay, what I'm trying to highlight here is the complete response of current flowing through the inductor. The complete response of current should be given by this, or you should write your complete current using this equation. Okay, you should know this one is ISS or I short circuit, I steady state, and this one is your I initial, and you also need to calculate what is your tau. So if you have these three parameters, then it is the equation of current flowing through the inductor is complete. And maybe if you don't understand this, what do you call it, response, also okay at the moment, because the response that showed over here is based on this equation. And remember that if this term, maybe if I, what would happen if p equals to infinity? What happened over here? E to the power of infinity. What does it give us? This element, okay, this element will become 0, right? And 0 plus ISS, okay, I steady state is given by this part. So that's why towards t towards infinity, if you substitute t equals to infinity in this equation, you will find that all these terms, okay, the second terms over here equals to 0, and you will end up only this value. So that's why you see here the value starting from I naught reduced, decaying, reduced towards the value of our steady state current flowing through our inductor. Okay, and if the initial current is 0, okay, if you don't have any initial current, meaning that it will be a lot more easier. the terms over here is equal to 0, and your final equation of I of t is given by this equation. If you only remember equation, sometimes you will get it right, but sometimes you're not going to get it right. But if you understand that, okay, this is the response that I would like to have, and whatever value of I, whatever value that available over here, I just put it over here, then you should be safe. But if you just, okay, for this condition, this is the equation. And for this condition, this is the equation. Maybe sometimes you will get it right, but maybe you will not have a always right in terms of if I change the arrangement of the circuit, maybe you will might put it wrongly. All right. Anyway, this is the current and voltage response with no initial current. So the current will be given like this, okay, and the voltage will be given like this. This is basically vice versa due to the nature of the current originally. All right, we move on into example 7.12. Okay, and we only have around 15 minutes to, I only have 15 minutes to explain on this. Right, 7.12. Okay. All right. The idea of solving first order circuit, either source free or with step response, is always the same. The first thing that you need to, actually it has 3 steps. The first one is finding your initial properties or initial parameters at t less than 0. Later on, you start working on the t greater than 0, but to find what is the value of tau. And then also the third step, basically try to write down back your equation. Write down means that you need to write this kind of equation. Since you already know what is the value of I naught and I infinity and also tau, you can write your equation back. Okay, now, according to the example, it says here, find I of t in the circuit for t greater than 0. Assume that the switch has been closed for a long time. We need to find what is the current flowing through this inductor for t greater than 0. Although it says here t greater than 0, you also need to analyze t less than 0 as well. Okay, don't forget about that. And here it says, assume that the switch has been closed for a long time. If the switch has been closed for a long time and open at t equals to 0, if this is closed for a long time, what happened to the circuit? Basically, the circuit at t less than 0, we should have this kind of circuit. And this is, okay, this is where okay, this is where the short circuit happened. due to the switch over here being closed. So this resistor is 2, this is 1/3 Henry, and this is 10 ohms. Okay, if you consider this kind of circuit has been kept in this arrangement for a long time, meaning that this inductor will behave like a short circuit. Means that actually you're going to have a circuit which looks like this at t less than 0. So this is I naught, okay, I initial that you need to find. Okay, this is I naught. And to find I naught, it is basically based on voltage, based on Ohm's law, where I naught can be found by looking at this voltage divided by this 2 ohm resistor, and then you can find this value, current flowing through this part. So that's why here, you see here, current through the inductor at t equals to 0 negative, before the switch is open, or before at t less than 0, is given by this equation. Because the inductor current cannot change abruptly, means that at t equals to 0, the current still in that direction, and it cannot change to another value. It will, we need to analyze what happened, what's going to happen next. I mean, what's the circuit looks like after the switch is open, or at t greater than 0. Okay, at t greater than 0, looking at the circuit should look like this. This is just after the switch is open. Oh, I don't like this. Okay, I saw it again. Ooh, very bad. Okay, this is what we have at t less than, greater than 0. This is 2, this is 3 ohm, and this is 1/3 Henry. This is for t greater than 0. Okay. At t greater than 0, what we expect to find? First, we try to calculate tau. Second, we try to calculate what is I infinity. Okay, I infinity. Okay, tau. If you try to calculate tau, what you try to do here, you try to remove this terminal. This terminal should be removed, and if you remove, okay, it will look like this. Okay, this is the short circuit part. And this is your resistor 2 and 3. And you try to find what is the value of R looking from that terminal. So that's what you're gonna do. So that's why here, you see, for RTH, it is given by 2 plus 3 because of this kind of circuit arrangement. And for I infinity, Okay, for I infinity, you should consider your circuit should be looks like this. And remember, if we kept this kind of circuit for a long time, means that it will reach the steady state condition for this inductor, and the inductor will behave like a short circuit. And what we need to do is we try to find what is the, this is wasting my time here. This part is short circuit, and we try to find what is the current over here, I short circuit, or current here, I infinity. Okay, maybe I remove this. Oh, cannot remove that one. Yeah, okay. The inductor over here will behave as a short circuit, and the I infinity that we try to get is actually the current flowing through here. And the current flowing through here is given by the voltage divided by the resistors we have. Here is 2 and also 3 ohm resistor. That's why you see here, for I infinity, we use voltage divided by the resistor. Resistor is 2 plus 3 and given by 2 ampere. Since we have this I naught, I infinity, and also RTH, and later on using this RTH, finding the tau, you can write down your equation as this, using that equation. So you have I infinity plus I naught minus I infinity e to the power of negative t divided by tau. And the rest will be the checking part. But actually, if you reach this one, it's all done. Okay? Now, what do you expect in your final exam question is something which is look like this. And this is for step response RC circuit. Maybe I can also ask about step response RL circuit as well. So this is what you will expect in your final exam. So in summary, the way we analyze first order circuit, what we need to do is try to follow the procedure, follow the parameters that we need to identify based on the final equation that should be in flowing through our inductor or voltage across our capacitor. That's the what you say, the general idea on how to solve first order DC circuit. Okay, if you find this one is hard, next week you will find the topics is harder than this. Okay, and that's why I really hope that you don't let towards the end and try to revise back about this content. Yes, of course you need to prepare for your test, but bear in mind during your call it semester break, please have a look at this topic back so that you're not gonna miss a lot towards the end of the semester. Okay, I think that's the end of first part, first order DC circuit, and next week we will get into our second part, more challenging stuff. The second order circuit, where in our circuit we have RLC, combination of resistor, inductor, and also capacitor. So that's why it is called as second order circuit. And as usual, please do pre-reading on this topic so that you're not gonna attend this session blank. So you should have some basic idea on what's going on, what do you what to expect in this topic. All right, thank you from me. Um, and I think I will stop sharing. Uh, have you what do you call it? Fill out the Google form for attendance?
No, not yet.
Yes. Yes.
Okay,
Yes.
thank you so much. And as usual, this is the part where we try to snapshot